Hello students, welcome to MEC 1321 Engineering Statics. Today we're going to start going over Chapter 5, which is titled Equilibrium of a Rigid Body. In this video we're going to do sections 5.1, which are conditions for rigid body equilibrium, and sections 5.2, which are 2D free body diagrams. So let's go ahead and get started with section 5.1, conditions for rigid body equilibrium. A rigid body is a body that does not deform under applied load. It's a body that remains rigid. We also know that in statics that there is a requirement that a body is considered static if it has no acceleration, so acceleration is equal to 0, and it either has a velocity that is constant or a velocity that is 0. Now, remembering from physics that force is equal to mass times acceleration, we find that with static problems that force becomes equal to 0 because acceleration is 0. So, say we're given some arbitrary geometry. Let me move this to the side here and make it black. Say we're given some arbitrary geometry. It has a number of force vectors that are coming out of its body. It also has a number of couple of moments that are applied to it. And there's some point O of interest at which we want to find equilibrium. And it has an acceleration equal to 0, and a velocity equal to a constant. Well, then the conditions for equilibrium will be that the resultant force, which is equal to the sum of the forces, is going to be equal to 0. It's also a requirement that the resultant moment about point O, which is equal to the sum of all of the moments, all the coupled moments within the body, is going to be equal to 0. And these two equations are called our equations of equilibrium. And these equations must be satisfied if we're assuming a body is a rigid body as well as it is a static body. Now, remembering from Chapter 4, where we go over equivalent systems, we know that we can take this system of forces and moments and simplify it into a single resultant force and coupled moment at some distance a. And if we do that, then we'll find that the conditions of equilibrium, these two equations, are equivalent to the sum of the moments about point A, where r is a distance from A to O cross FR, plus the coupled moment r about point O. And that will be equal to 0. Now note that in this class, we typically will only, in the examples that I show as well as on the exam, we will focus on the traditional equations of equilibrium, which is the sum of the forces equal to 0 and the sum of the moments equal to 0. You will not really see any equivalent system type problems that will be required from me. However, you can use this equivalent system equations if you choose to, but it's simpler to use the two independent equations, and you'll see in class when we do examples. So now that we've gone over what are the equations of equilibrium and what are the requirements for them, let's go into how do we actually idealize a body. How do we take some geometry and get to the point where we can apply the equations of equilibrium? And that's where we go into section 5.2, which is free body diagrams. So it states here, before applying the equations of equilibrium, we must idealize the problem by creating a free body diagram. To do this, the shape of the body is isolated, i.e. freed from its surroundings. At the same time, the known and unknown external forces are identified. So what we've done is we've taken the real world, so an image of a real world structure, and simplified it, removing all of the volumetric information and all the distracting things, and leave only the force vectors and the couple moments and the positional information that will allow us to solve the problem. And at that same time, we identify the things that we know about, the quantities we know, and also the unknown quantities, those unknown external forces that we need to identify. So the classic example is a simple hanging weight, where here we have a mass that's hanging by two cables and it's attached to the roof. And we're given the mass, the quantity of the mass for that object, that body. So let's start crafting the free body diagram. The first thing we want to do is we want to free the body. We want to remove those distracting things. So, we can look at the connection point between the links and the mass, and we can say that's the point of interest we want to find. That's where the forces are, the known and unknown forces are meeting. So we can put a point and then say, okay, that's point O, that's our point of interest. And then we can draw our coordinates, so say the X direction here, and then this is the Y direction. Then we, at the same time, need to indicate our known and unknown forces. Well, we're given the mass. We can assume that there's gravity. So we can say that there's gravity acting because it's attached to the roof. And we know that mass times gravity gives us a quantity of force, which is weight. So we have a known force, which is the mass times gravity. And then we look at our unknowns, which are the reactions that develop due to the cables, the force in the cables. So we can say there's a reaction 1 and 2, which are related to cable 1 and cable 2. So now we've created the free body diagram. We've put in the knowns and the unknowns. The next step is to examine the free body diagram and try to identify the angular information, the information that relates these knowns and unknowns to each other. So in this case, maybe we want to find the angle between R2 and the x-axis, or maybe we want to find the angle that is between R1 and R2, because this type of information will be useful when we actually start to apply our equations of equilibrium. So once we've filled in as much information as possible in our simple free body diagram, our beautiful free body diagram, then we can start applying the equations of equilibrium. And it'll become very easy and very clear what equations we need and how we can apply them when we have an excellent free body diagram. It's also important for you not only to draw your free body diagram, but also to list your knowns and unknowns. By listing them on your solution, like listing them on the paper, it'll constantly remind you, what are you seeking? So as you go through and exercise those equations of equilibrium, you'll never forget, or you won't forget, oh, I'm supposed to be finding R1 and R2, or I'm supposed to be finding this, or finding some angle. By listing it, it makes it easier for you to, you don't have to hold it in your mind. You can constantly reference it as you solve equations. So to craft your free body diagram, what we have to do is free the body from its supports, free it from its surroundings. And in order to do that, we have to replace those supports with the unknown external forces that develop due to them. So support reactions are the unknown external forces that support a body. And there are two general rules for identifying what type of, or the type of external forces that will be developed due to a support reaction. The first rule is if a support prevents the translation of a body in a given direction, then a force is developed on that body in that direction. So a classic example is a roller. Say you have a beam, and in between the beam and the floor, there is a rolling ball. Well, if we were to try to apply a force or a load, or try to move the beam in the X direction, it'll slide across the roller and it's allowed to translate. But if we try to move the beam in the Y direction, downward, then a support, it is prevented from translating due to the support. And that prevented translation is due to a support reaction. And in this case, the support is Ry. The reaction is Ry, which is in compression. Another example is a pin, where you have a rigidly attached to the floor pin that allows rotation, so it can, it's a pin, so it can rotate around, but it cannot translate in the X or in the Y direction. And that prevented translation is due to support reactions Rx and Ry that develop. So we remove the supports and replace them with the reactions. The second general rule is if rotation is prevented, then a coupled moment is exerted on a body. A classic example is a fixed support, a beam that is fixed to the wall. So think a bookshelf that's rigidly attached, embedded in the wall, right? Well, or you could think stairs, right? Stairs are rigidly attached onto the wall that you walk up. Now, if you take that support, which is a fixed support, and you want to idealize it and replace it, well, then think about the beam. If we wanted to move the beam in the X direction, it would not move, it would resist. If we wanted to move it in the Y direction, it would resist. And if we applied some force at the end of the beam, then it would create a moment that needs to be counteracted. And so there must be a coupled moment that prevents the rotation of the beam. And so in the case of the fixed support, we have forces Fx and Fy, but we also have this moment M, this reaction moment that develops at the end of the beam. So in general, there are many, many different types of support reactions. All of the support reactions, every type of support can be replaced with a reaction force and or moment. Okay? The difficulty becomes identifying, what are those support reactions, right? Because every support does not have the same number of reaction forces or same number of moments. Some don't have reaction moments. Some only have one reaction force. So it's important for us to be able to identify. Now, in general, we can use the two rules that we discussed, but also just to give you examples, I'll show you many of the type of support reactions that you'll see in this course. And this is going to take quite a bit of time to get through these, so do bear with me. So a classic example is a cable. With a cable, the body is restrained in the directed along the direction of the cable. And cables only support tension. And a simple example of this is, say you have a weight and it's attached to the roof, or it's attached to your hand, right? If you let go of the weight, there's going to be a tension that develops in the cable. Now, if we were to take this same system and turn it upside down, so you have the mass above your hand and there's a cable, and you let that mass go, the cable is not going to support any weight. It's not going to support any compression. And so this just is a demonstration that cables only support tension, where that tension is coming out of the body. Okay. Another example: a weightless link. A weightless link is a rigid body. So the body is restrained in the direction along the link, but because the weightless link is a rigid body, it supports both tension and compression. Okay. Now let's go on to a roller. With a roller, the body is restrained perpendicular to the surface. So so if we look at this example, we have theta here. Theta could be 0, 90 degrees. It could be any quantity. But no matter what quantity it is, the body is restrained perpendicular to the surface. So a force is going to develop perpendicular to the surface upon which the roller rolls. And that force is going to be in compression. Now let's look at the example. Let's look at the example of a roller or a pin confined in a smooth slot. So in this example, there's a roller slash pin, but there's a slot, a channel that it travels along. In this case, the body is strained perpendicular to the slot, and the reaction force that develops can be either in tension or in compression. Where if the force is going into the body, it's under compression, and the force is coming out of the body, then the body is in tension, right? Tension, you're pulling it apart, so there's a force coming out. Compression, you're pushing in, so there's a force that's opposite that compressive force, okay? Another example is a rocker, which is a kind of different type of geometry. In this case, the body is restrained perpendicular to the surface. It supports compression, and so the force develops perpendicular to the surface. Okay. Another example is a smooth contacting surface, where the body is smoothly in contact with some surface. The body is restrained perpendicular to the surface. A force develops perpendicular to that surface under compression. Now let's look at the example of a member that is pin connected to a collar on a smooth rod. So in this case, just to clarify, there's a collar. Well, that's not bright enough. Let's use yellow. Well, that's not good either. Let's use red. There's a collar here, and then there is a pin on that collar. So we can see that the body is free to rotate about the collar, but the body is restrained perpendicular to the slot. So it can only move along the slot. And thus, either a tensile or compressive force will develop perpendicular to the orientation of that smooth rod upon which it travels. Okay, and now let's look at the last three here. The smooth pin we already went over. It's rigidly attached to the floor. It's free to rotate, but it's restrained. The body is restrained in both the X and the Y direction. And in that case, we develop the components, two component forces, Fx and Fy, which are directed along the X and Y direction. And we can replace those components with a force resultant F at some angle phi, which is relative to the x-axis, or relative to the y, either or. Another example is a member fixed connected to a collar on a smooth rod. In this case, the member is fixed connected and not pin connected, so the member can't rotate about the collar. And it's also restricted to travel. The member is restricted or restrained in the direction perpendicular to the rod, and it cannot rotate. Due to that, we know that there's going to be a force that develops perpendicular to the rod, but we also know that there's going to be a moment that develops because the member is not able to rotate about the rod. And the final example is a classic example, and this is one you should never forget, which is a fixed support. In this case, the body is restrained in both the X and Y direction, and it also is unable to rotate. So what we end up with is the component forces Fx and Fy in a coupled moment, which is also equivalent to a force resultant at some angle of phi in a coupled moment. And so it's important for you to become familiar with these different type of supports and the support reactions that do develop in each of these types of supports. In particular, to me, it's important that you know how to use the two general rules, which is a translation and rotation rule, because sometimes it won't be readily apparent what type of support reaction it is. And sometimes you'll need to actually think, okay, well, the support, this is supported, that is supported. So it's important to get very comfortable with using the theory and not just trying to memorize the support types, okay? So the procedure for analysis, the procedure for actually constructing and setting up a free body diagram is as follows. First, you draw an outline of the shape. So you take whatever the system is and you try to idealize it and free it from its surrounding. Free it from its constraints and connections, and draw a sketch of the forces, the known and unknown forces that develop. You need to identify all the known and unknown external forces and the couple moments that are acting on the body. And so you'll encounter things such as applied loads, which are the things that are given, the reactions that occur in supports and contacts within the body, those are the unknowns, and then also the weight of the body. If you're given a mass, then you can assume that the body will have a weight due to that mass. If you're given a body that doesn't have any mass, then you can assume that there is no weight, okay? And this information will be in the drawing, in the diagram. And so you need to very carefully study the diagram and craft and identify those internal, those unknown and known external forces very quickly. Once you've identified them, the forces and the coupled moments need to be properly labeled, to label their magnitudes, determine their directions, and use nomenclature, or like, I'll call this force A and force B. Use consistent nomenclature so that when you start applying your equations, you remember what force vectors you're actually dealing with, what angles you're actually dealing with. It's also important to establish what is your coordinate system, and also input not only the angular information but the dimensional information. How far is this force from our origin? At what angle is this force to our origin? And once you've crafted your free body diagram and you feel comfortable with it, then sit and analyze it. And most of the time, when you sit and analyze it and you have a well-crafted free body diagram, you can readily determine missing information, like angular information between force vectors or information about what type of moments will develop. And it makes it easier to visualize what type of system you have and how you can reach equilibrium. With that being said, I did not cover everything that is in section 5.1 and 5.2. So it's important that you take the time to read the book and review the notes pertaining to these two sections. And if you do that, you'll have a great experience on the quiz which follows this video. Do take a little bit of time, maybe try to do some of the examples or fundamental problems for this section, and you'll do fine on the quiz. Thank you for your time. I'm Dr. Stewart.